I want you to take a second and just imagine the microchip inside whatever device you were using to listen to this right now.
Yeah, the literal hardware running the audio right now.
Right, exactly.
Yeah.
And if you were to crack that device open, which, I mean, please don't do that.
Also, definitely do not do that. It voids the warranty.
Seriously. But if you did, the chip just looks like a tiny, flat, sort of gray square. But functionally speaking, if you could zoom in close enough, it is this sprawling, like impossibly complex metropolis.
A completely alien city, yeah.
We are talking about tens of billions of microscopic transistors, all layered on top of each other, connected by this insane three-dimensional highway system of copper wiring.
It really is staggering when you think about the scale of it.
It is. And the question is, how do computers actually map out a city that small and, that incredibly dense without just totally crashing?
Because you would assume it requires massive, like supercomputer level calculations just to place every single millimeter of material, right?
Exactly. But we are doing a deep dive today into the documentation and presentation slides for a new Python library called PhysDesPy.
Which is built specifically for computational geometry and chip design.
Right, and looking at this source material, it turns out the secret isn't just throwing more brute computing power at the problem.
Not at all. It is actually a very strict, almost bizarre set of geometric rules.
Because it is a phenomenal engineering challenge. You are essentially trying to play the world's most complex game of Tetris.
Yeah, but a game of Tetris where the pieces are measured in nanometers. And, a single microscopic overlap means your entire multi-million-dollar silicon wafer is just a really expensive paperweight.
Right. So to prevent that, the sources say you can't just use standard geometry.
Right, because, think back to high school math class. A polygon can look like almost anything.
Sure, a triangle, a star.
Yeah, a random jagged shape with angles of 45 degrees or 12 degrees or whatever you just happen to draw on the paper.
But the geometry powering this software, PhysDesPy, it relies entirely on something called a rectilinear polygon.
Exactly, rectilinear.
Which basically means no diagonals allowed, right?
None at all, zero diagonals. A rectilinear, or you might hear it called an orthogonal polygon. It's a shape where the edges are exclusively horizontal or vertical.
Okay.
Every single interior corner is strictly 90 degrees or 270 degrees. Nothing else is allowed.
See, I have to say, looking at this from a pure, design perspective, that feels like a totally artificial constraint.
How so?
Well, if I'm designing a chip and I need to connect point A to point B, the absolute shortest physical distance is just a straight diagonal line.
Right, as the crow flies.
Exactly.
Okay.
Forcing everything into this jagged staircase pattern, it's like driving a taxi that can only take left and right turns up and down the avenues of Manhattan.
The Manhattan analogy is actually perfectly accurate here.
But it seems wildly inefficient for the actual electrical signals, doesn't it?
Yeah.
Like, why make the path longer?
It definitely seems that way until you look at the actual physical manufacturing process of VLSI, which is very large-scale integration.
Okay, lay it on me.
So a modern microchip isn't just a flat piece of paper. It is built in vertical layers. You have these distinct metal routing layers stacked on top of the silicon.
Like floors in a skyscraper.
Exactly. And to prevent crosstalk, which is signal interference, and to prevent manufacturing errors, these layers are heavily directional.
Oh, I see where this is going.
Yeah. So metal layer 1 might run exclusively north-south, and then metal layer 2 runs exclusively east-west. So if you try to route a physical diagonal wire through that, you are actively violating the physical constraints of the manufacturing machinery itself.
So the rectilinear math isn't some arbitrary software rule at all.
Not at all. It perfectly mirrors the actual Manhattan routing grids that physically exist on the wafer.
The software is literally just speaking the native language of the hardware. Okay, so we have these strict rules for our tiny digital city blocks, only 90-degree turns. But wait, if I'm designing a chip with 10 billion of these blocks.
Which is a standard number these days.
Right. And I try to drag and drop a cluster of them across my screen. Wouldn't my computer just completely freeze trying to recalculate the coordinates of all those little jagged corners?
That is the classic memory bottleneck in design software, yeah. Moving complex shapes is incredibly heavy on memory.
So how is PhysDesPy avoiding that?
By fundamentally changing how the shape is stored in the computer's memory in the first place.
Okay, how?
Think about it. If you try to store the absolute global coordinates of every single corner of a billion shapes.
Like X is 100, Y is 200?
Right, and the next corner is X 150, Y 200, and so on. Every single time you nudge that component, The processor has to load millions of distinct numbers into its cache, recalculate every single one of them, and then write them all back to memory.
Which would absolutely bring the system to its knees, especially during what the source calls the incremental placement phase.
Yeah, that phase is brutal.
Because that's where designers and automated algorithms are constantly nudging components around to find the absolute optimal fit.
Precisely. And that is why FestisPi uses a totally decoupled data structure.
Decoupled how?
So in the code, this is handled by a class called rPolygon. And an rPolygon shape only tracks two things.
Okay.
First, an origin, which is just a single absolute reference point on the main grid.
1 point.
Just one. And second, an array called vex, which is a list of edge vectors that are entirely relative to that origin.
Oh, wait, so the array just reads like a set of driving directions.
Exactly. It's like start at the origin, go right 10 units, go up 5 units, go left 3 units.
Until the shape just closes back on itself.
Yes. The geometry is entirely relative.
That is brilliant. It's like having a highly complex architectural blueprint, but it's pinned to a corkboard.
Oh, I like that analogy.
Right. The drawing itself is the vector array. So if I decide I want to move the entire house I'm designing to a different part of the map, I don't erase and recalculate every single wall on the paper.
No, you definitely don't.
I just pull the single pin out of the corkboard and stick it somewhere else.
And mathematically, pulling that pin translates to what we call O1, complexity, constant time.
Meaning it's basically instantaneous.
Yep. The computer performs a simple in-place arithmetic adjustment on that single origin coordinate, the massive array of relative vectors. It remains totally untouched.
Wow.
So you experience virtually zero cache misses in the CPU, which means you can slide incredibly complex geometric shapes across your digital silicon wafer without any lag.
Okay, so now that we can move these massive shapes around instantly, we have to talk about how we actually measure them.
Right, because moving them is only half the battle.
Exactly. Because anytime you introduce geometric calculations like finding the exact surface area of a really sprawling polygon, you usually end up dealing with decimals.
Inevitably, yeah.
And a rounding error in a microchip isn't just a typo on a screen. It results in a literal physical short circuit.
And that is the exact reason the developers of FestisPi outright banned floating point arithmetic for area calculations.
Wow, just completely banned it.
Yeah. Floating point numbers, which are basically how computers handle decimals, they inevitably introduce these tiny little approximations at the far end of the decimal point.
Which I guess is fine for a video game, but
totally unacceptable at the nanometer scale of a microchip. So to find the exact area without decimals, the library implements something called the shoelace formula.
Now, I'm vaguely familiar with the shoelace formula for, like, simple triangles.
Sure.
But how does it work for a sprawling, snake-like rectilinear polygon without defaulting to messy decimals?
Okay, visualize this. Imagine dropping a vertical line from every single point on your polygon straight down to the x-axis of your grid.
Okay, so I'm drawing little pillars straight down to the floor.
Exactly. Now, for every edge of your shape, you calculate the area of the rectangle or trapezoid formed between that edge and the floor, the axis below it.
Got it.
As you trace the top edges of your shape, moving left to right, you just add those areas together.
Okay, but wait, if I do that, I'm capturing the shape, but I'm also capturing all the empty space sitting underneath it, right?
Right. You have a massive oversized area value at that point. But then as the perimeter loops back around and you start tracing along the bottom edges, your vectors are moving right to left.
Oh, so the formula subtracts the areas of those lower rectangles.
The empty space perfectly cancels itself out. The only mathematical value left over is the exact internal area of the polygon itself.
That is so elegant. And because our rectilinear shapes are strictly locked to the Manhattan grid, every coordinate is a whole number anyway.
Exactly. The entire massive calculation is done purely with integer multiplication and addition.
So total precision, 0 floating point drift.
0.
But wait, for that adding and subtracting trick to work, the computer has to know the orientation of the shape.
Ah, yes. It absolutely does.
Like it has to know whether the path tracing the perimeter is moving clockwise or anti-clockwise.
Yeah.
Otherwise, it might subtract the top and add the bottom, and you'd end up with a negative area.
That is exactly what would happen. Orientation is everything in computational geometry. To a computer, a shape isn't a drawing, it's just a void on a grid.
Right.
So knowing the sequence of the edges clockwise or counterclockwise is literally the only way the algorithms can deduce what is inside the shape versus what is outside.
So how does FSD's pi lock that orientation down?
It relies on finding a very specific anchor, the bottom leftmost vertex.
Bottom leftmost. So out of all the thousands of corners, it searches for the absolute lowest y coordinate.
Yep. And if there's a tie, like if there's a flat bottom edge, it picks the one furthest to the left on the x-axis.
Okay, so it gives the algorithm an unambiguous anchor point to start its trace.
Precisely. You always know exactly where you're starting.
Okay, so that handles the basic math for finding the area of simple shapes. But reading the sources, the components on a VLSI chip are rarely simple rectangles.
Oh, almost never.
Right, they wrap around other components, they snake through tight corridors, they form these massive, chaotic blobs.
We call them monolithic geometries.
Monolithic, I like that.
I like
And
it.
to process those monoliths, the documentation introduces a concept called monotone polygons.
Yes, the monotone master key.
Okay, so what does monotone mean here? Because I'm just thinking of a really boring speaker.
Well, it's monotonic in the mathematical sense. A shape is considered monotone if you can draw a straight line through it in a given direction, and it intersects the shape's boundary at most twice.
At most twice. Okay, give me a visual for that.
Think of an X-monotone polygon. Any vertical line you drop straight down through the shape will only cross the boundary as it enters the top and as it exits the bottom.
So it will never weave in and out of the shape multiple times.
Right. The perimeter never spirals back on itself horizontally. It effectively separates the entire complex boundary into two distinct, non-overlapping chains.
So you have an upper chain of edges moving left to right and a lower chain moving left to right.
Exactly. And a Y monotone polygon does the exact same thing, just vertically splitting it into leftmost and rightmost chains.
Got it. And the sources say any complex non-monotone shape can be mathematically sliced into smaller monotone pieces.
Yes, any shape can be broken down this way.
Okay, I have to stop you here because I'm stuck on this slicing step.
What's the holdup?
Well, we just spent all this time talking about how the origin and the relative vector arrays save memory, right? Keeping the data structure incredibly lightweight.
Right, the O1 translation.
Yeah. But now you're telling me we took a perfectly good, completed component shape and we run a whole separate algorithm just to artificially slice it into upper and lower chains.
We do.
Doesn't that sound like we are adding massive, unnecessary computational overhead just to keep our virtual desk organized?
It completely looks like overhead at first glance, until you realize the alternative is a processing bottleneck that literally brings the system to a halt.
Okay, why?
Because when a standard algorithm processes a complex, unrestricted polygon, it constantly has to backtrack. Think about it. If the shape spirals inward, the algorithm has to verify that an edge on the left side doesn't secretly intersect an edge it already processed on the right side.
Oh, wow. So that means comparing almost every edge against every other edge in the whole shape.
Exactly. Which pushes your computation time into an exponential nightmare. The bigger the shape, the time it takes to process it just absolutely skyrockets.
But by filtering the shape into monotone chains first,
you reduce the complexity of all subsequent algorithms to linear time.
Linear time. That is huge.
It is the ultimate mathematical shortcut. Because in X monotone chains, X coordinates are strictly increasing from left to right, the algorithm never has to look backward.
It just strolls down the chain, processing each vertex exactly once, knowing it won't hit itself.
Exactly. One pass, nice and easy.
Okay, so we take a slight performance hit up front to organize the data into chains, and it unlocks incredible linear speed for the heavy lifting down the line.
That's the trade-off, and it's totally worth it.
And the sources highlight two major applications of this monotone logic. The first is generating a convex hull.
Yeah, this is a fun one. If you have a scattered, messy set of coordinate points, a convex hull is like snapping a tight rubber band around the outside of all those points.
So it creates the smallest possible enclosing boundary. It effectively shrink wraps the data.
Shrink wraps is a perfect way to describe it.
And the library creates this shrink wrap using a very specific two-pass pipeline, right?
Yes. Pass 1 sweeps through the raw point set and reduces it into an X monotone shape. So that sweeps away all the vertical concavities, or the dents.
Then pass 2 takes that output and immediately reduces it into a Y monotone shape.
Right. And because the shape is forced to adhere to both monotone rules sequentially, the resulting geometry is physically incapable of having any inward-pointing dents at all.
Wow.
It is mathematically guaranteed to be a fully convex polygon.
And crucially, FizzBack executes this pipeline using a doubly linked list behind the scenes.
Which is such a smart implementation detail.
Why is that so important?
Because a doubly linked list allows the algorithm to quickly traverse back and forth between adjacent vertices locally, so it can smooth out the boundary without ever having to restart the search from the beginning of the array.
It just saves so much time.
Exactly.
Now, the second application of our monotone master key is the raycasting algorithm for point inclusion.
Point inclusion, yeah. This is critical for verification.
Because this is how the computer verifies if a specific transistor, or via, is sitting safely inside a valid region, or if it has been accidentally placed outside in a forbidden zone.
Right. And to test a single point, the software mathematically casts an infinite straight ray. It originates from that exact coordinate, and it shoots out horizontally in the positive x direction toward infinity.
I love the analogy for this. It's like walking in a straight line through a house.
Oh, the light switch analogy, yes.
Right. So every time you cross a wall, which is an edge of the polygon, you flip a light switch.
Right.
So you cross one wall, the light is on your end, which means you are standing inside a room. But if you keep walking and cross a second wall, you flip the switch O off F, which means you have passed through the room and you are back outside in the yard.
Exactly. So an odd number of wall crossings means you are inside. An even number means you are outside.
Odd count inside, even count outside. It is so simple.
And because the shape is already monotone, the algorithm doesn't have to test the ray against every single edge of a massive shape. It only checks the edges that fall within the specific x-coordinate range of the point.
Just traversing linearly.
Exactly.
Okay, but wait. I have a question about this.
Sure.
What happens if your test ray happens to hit exactly on a corner vertex? Think about the light switch analogy. If I walk dead center into the corner where two walls meet, did I just cross one wall or two walls? Did I cross a boundary at all or just brush past it?
That is a brilliant catch. In computational geometry, a point landing exactly on a vertex is the classic edge case that ruins algorithms.
Really?
Oh, yeah. Because if the computer counts it as hitting two edges simultaneously, your parity flips from odd to even.
And the computer suddenly thinks the coordinate is outside the shape when it's actually still inside.
Exactly. A false negative.
So how does the library handle that without bogging down the system with, like, a million complex exception rules?
By employing a really elegant mathematical trick, often referred to as an epsilon perturbation.
An epsilon perturbation.
An epsilon perturbation.
Or a ghost ray.
Ghost ray sounds way cooler. Let's use that.
Okay, ghost ray it is. So the math treats the test ray as if its y-coordinate is shifted up by an infinitesimally small fraction in epsilon.
Oh, I see.
So functionally, the ray passes just microscopically above the exact corner vertex.
So it totally misses the corner itself.
Right. Therefore, it only actually intersects the specific vertical edge that extends upward from that corner, and it completely ignores the edge that extends downward.
That is genius. It preserves the odd-diven parity perfectly. The light switch only flips when it is absolutely mathematically required to.
It keeps the math perfectly strict without any messy code. Incredible. So everything we've discussed so far operates with this incredible efficiency, keeping our processor speed fast.
Mostly ON, or O1 time.
Right, but the presentation slides reveal that physical chip design has one inescapable heavy-duty chore that just breaks this linear streak.
Ah, yes. Convex decomposition.
Otherwise known as polygon cutting.
Yeah.
We've talked about how VLSI routing generates these massive, sprawling, concave shapes.
Monoliths.
Right. But the physical manufacturing machinery and the standard cell placement algorithms, they cannot always digest monolithic geometry.
They choke on it.
So sometimes you must forcefully convert a huge snake-like polygon into a neat set of smaller, primitive convex rectangles.
Right, you have to chop it up.
And to slice the polygon into rectangles, the software sweeps through the boundary hunting for pinch points.
Pinch points.
And because we are working exclusively with rectilinear shapes, a pinch point is always exactly a 270-degree inward turning interior angle.
It's essentially a dent in the shape.
Exactly. And to find that dent within a list of vectors, the software analyzes the dot product of the adjacent edges.
Right, the vector math. As the algorithm walks the perimeter, it evaluates the directional vector of the edge it's currently on and compares it to the vector of the edge it is turning onto.
So if you are tracing the outside of a normal rectangular box, you are always turning in the same direction. Let's say you're always turning right.
Right. And every right turn is a 90-degree internal angle.
So the vector math spits out a consistent sign for that orientation.
Yep. Positive or negative, it stays consistent.
But the moment the perimeter folds inward into a dent, the boundary forces the path to make a left turn.
And the mathematical sign, that specific vector calculation, instantly flips.
Boom. The algorithm detects the reverse sign and flags the 270-degree concavity instantly.
Exactly. It spots the dent.
And once it flags that pinch point, it slices the shape right at that vertex, extending a cut line until it hits an opposite wall.
Slicing the monolithic shape into two smaller pieces.
And then it recursively runs the entire check all over again on the new pieces until absolutely 0 pinch points are left.
Which works beautifully, but
the performance dashboard in the documentation shows a massive warning sign here.
yeah, it does.
The worst case time complexity for convex decomposition scales at ON2.
The dreaded n squared.
Ouch! As my computer science friends would say, that does not scale well.
Not at all.
The bigger and more complex the shape, the exponentially slower the algorithm runs because of all that recursive array splitting and rechecking.
It gets very heavy, very fast.
But wait, we spent this entire time avoiding exponential overhead. If recursive polygon cutting is so heavy and bogs down the CPU, why do we even bother doing it?
I know, it seems counterintuitive.
Why not just leave the shape intact?
Because that worst case scenario cost. It is an absolute unavoidable necessity for hardware execution.
Why?
In modern chip design, you have to place standard cells into the layout. Standard cells are the tiny pre-designed logic gates, like NND gates and OR gates.
The actual brains of the chip.
Exactly, and the photolithography tools and the software that manages these cells, they require what are called legalization regions.
Legalization regions, meaning perfectly defined bounding boxes to know exactly where a transistor can legally sit without causing a short circuit.
Precisely. If you hand the legalization software a massive, concave, spiraling polygon, it literally doesn't know how to physically pack the discrete rectangular logic cells into it efficiently.
It gets confused.
It does. The placement algorithms absolutely require valid, non-overlapping primitive rectangles to function. You literally cannot physically manufacture the logic on the silicon without the bounding boxes generated by this specific decomposition process.
Wow. Which brings all of this pure abstract math crashing perfectly back into the physical reality sitting in the palm of your hand right now.
It really does. Every concept we've unpacked today,
The memory-saving origin vectors,
the integer-based shoelace formula,
the monotone filters.
all of it is actively driving the core layout of modern technology.
The documentation explicitly maps these algorithms to the physical layout phases too. Floor planning the macro blocks of the chip relies on the vector translations.
Yep. Creating the legalization regions for standard cell placement relies on the convex decomposition we just talked about.
And global routing, where the software maps the wiring while avoiding physical obstacles, relies on ray casting and point inclusion.
Even area tracking, which is used to allocate the massive power grid stripes across the wafer to ensure every single transistor gets enough voltage,
Right.
that relies entirely on the precise floating point free math we explored.
It is just a stunning translation of software logic into manufactured architecture.
It's beautiful, honestly.
But there is a section at the very end of the FISD's Pi documentation titled Future Enhancements that really reframes everything we've talked about today.
Oh yeah, they are not stopping here.
Right. They have built this incredibly robust, mathematically airtight system for 90-degree rectilinear routing, but the developers are already looking beyond it.
They outline plans for implementing Minkowski sums.
Which are complex algorithms used for polygon offsetting.
Exactly. This allows the software to automatically generate precise, mathematically rigorous buffer zones around shapes to prevent signal interference.
So even tighter packing without the signals bleeding into each other.
Right. And they're also looking at advanced Boolean operations.
Which will allow the system to calculate the exact geometric intersections and unions of multiple overlapping polygons across different layers simultaneously.
It shows that the underlying engine is constantly evolving to handle more and more density.
And it leaves you with this incredible thought to chew on. As our physical manufacturing technology improves year over year.
Smaller and smaller.
Exactly. As microchips inevitably approach the literal atomic scale, where individual transistors are just a few atoms wide, will our geometric algorithms need to adapt and break these rules?
It's a fascinating question.
Or is this rigid 90-degree Manhattan grid we've explored today the ultimate unbreakable law of the digital universe?
I guess time will tell.
Definitely something to think about the next time you look at the device in your hand. We will leave you with that. Thanks for joining us, and we will see you on the next deep dive.